Hi, in this video we're going to look at another example of closed system, and the previous one is a rigid tank, which is when volume is constant, and here we're looking at a piston cylinder, and for this piston cylinder, since the mass of the piston stays constant, so the pressure inside, the weight of the piston divided by area, that's, it's basically force over area. That's going to be pressure. So since this weight stays a constant, this pressure is constant. So for this problem, it is a constant pressure problem. P1 is equal to P2, equal constant. So let's read out what we have here, and while we read out, we write down what's given. So piston device contains 0.85 kilogram of refrigerant, R134, and the initial temperature T1 is -10 degrees Celsius. The piston that is free to move has a mass of the piston P is 12 kilogram, and the diameter is 25 centimeter. Then the local atmosphere pressure is 88. So pressure is 88 kilopascal. Now the heat is transferred to refrigerant until the temperature now T2 is 15 degrees Celsius. Then they want us to find the final pressure, find the P2, right? It's final, so it's P2. And the change in the volume in the cylinder. So delta V, the change. Also the change in enthalpy of that, okay? Now let's take a look. How do we figure that out? And here I'm going to make a note. This is the pressure. This is the pressure of local atmosphere pressure. So it's like ambient pressure, 88 kilopascal. Okay, let's see how do we solve this. First one, the step. What do we know in the state 1? We know the T1. We know the initial temperature, and we also know the mass of the piston. So we can maybe figure out the pressure, right? The pressure inside. So P1 is going to be the weight, 12 kilogram times 9.8. That's going to be the in Newton. Then divided by the cross-section area. It's diameter 25. So we can use pi r square. R here, we can use pi d squared over 4. So however, d here, I'm going to use meter. 0.25 pi d squared over 4. In that situation, this will be unit of meter, and this will be unit of Newton. Then we'll get unit of Pascal. Let's see what we have here. So I have 2396.97 Pascal. That's the pressure. That's the pressure inside this piston, right? And if you change that, it's going to be 2.397 kilopascal. But here I'm going to correct what I just said. This is not actually the pressure inside, because we were given the ambient pressure. It's right here. So the pressure inside here, P1, it's really going to be this value plus this ambient pressure, 88 kilopascal. That's going to give us the total of the pressure inside right here. Because you have ambient pressure going down, you also have the weight going down. Together added up, that's going to be 90. Let's just use 90.4 kilopascal. Okay, so that's our P1. And we know this is a constant pressure problem, so our P2 is going to be equal to P1 equals 90.4 kilopascal. All right, now let's move on to look at our state 1. Our state 1, we know P1 now, which is 90.4. We also know T1 because that's given as negative 10 degrees Celsius. Then what do we need to find out? We need to find V and H because we are asked to find the change in those two. So we needed to find out our V1 and H1. Okay, so it's R134. We were given pressure and the temperature. When you have both, like I always encourage you to look at pressure table, like how we did it for steam table. So now let's look at the pressure table, which is table A12, right? And then look at table A12, we're going to look at 90.4 kilopascal. So it's around 90. And look at saturated temperature is negative 28. Well, so 90.4 is going to be around that value also for negative 28. And our temperature is what? Negative 10 degrees Celsius. So which is way, so here is our evaluation. Our negative 10 degrees Celsius is going to be way greater than the saturated temperature at 90.4 kilopascal. What does that mean? That means it is going to be superheated. So this R134, this freon, it's in vapor form. Since it's in vapor form, we're going to go to which table then? So from here, you start with A12 to make that judgment, and then you're going to go to table A13. At table A13, we are going to use those two values, negative 10 degrees Celsius and 90.4 kilopascal. 90.4 kilopascal is going to be how many megapascal? It's going to be divided by 1000, 0.0904 megapascal. 0.09. So that's around this value, right? 0.1. But it's not really 0.1. So this is another very good example to use linear interpolation here between those two pressure millitable. Okay, we need to find V and we need to find U. I'm sorry, V and H. And our temperature is negative 10. So if we are looking at negative 10, and we're going to extract some numbers out, okay? So the number we're going to taking it out will be, since it's going to be at a negative 10 degrees Celsius, but the pressure is between 0.06 megapascal and 0.1 megapascal. And from here, we're going to look at V, and we're also going to look at H. Our 0.06 megapascal, what's our V value? It's going to be right here. .35048. And what's our H value there? 248.58. Then we're going to use 0.1 megapascal, this value, 0.20743 for V, and H will be 247.49. That's our V and H. And remember, what we're trying to calculate is 0.0904 megapascal. So how do we do that? And here we're going to use linear interpolation. I'm going to go ahead and write down the equation right now to solve V. First, to solve V, I'm going to use 0.35048 minus 0.20743. The pressure 0.06 minus 0.1. You say, okay, we're getting a negative value. It's okay. but you have to be pair them up. For example, if I use this value, 0.34508, I have to corresponding to 0.06. Okay. All right, so we got that, and then we're gonna figure out the pressure here. For solve for V, if we're going to use, let's see, if we're going to use this V minus we're solving, 0.20743, and this V corresponding to what pressure? This pressure, 0.0904, and this volume is going to be corresponding to 0.1. Okay, then we can go ahead and solve our V. So pause, see what we got. So after calculation, I got 0.241762 meter cube per kilogram. Okay, so now we're going to use the same thing to figure out our H1. So solve H1, we're going to set up the linear equation as well. 248.58 minus 247.49, then corresponding pressure 0.06 minus 0.1, and here we're solving for this H1 minus 247.49, then corresponding pressure here it's 0.0904 minus 0.1, then we can find our H1. Let's see what we got. So now my enthalpy here is calculated as 247.7516. That's in kilojoule per kilogram. All right. Okay, so this is so far it's really good because we're learning how to get linear interpolation across the mini table. All right, now remember there's a mass given for this problem, right? And the mass is 0.85 kilogram. So we can figure out the total enthalpy H1 will be mass times H1. Then we can have our answer. So the answer is 210.59 kilojoule. All right, so that's our enthalpy H1. And if we want to find a volume, which we showed, because we know the specific volume, we're going to do the same thing times mass. We can figure out the volume 1 at a time. Okay, so big V1 is going to be 0.85 kilogram times our small V1. You can find the answer here. All right, now that's just stage 1, and now we're going to figure out stage 2. What do we know about stage 2? We know 2 things. We have to know 2 things. We know the T2, the temperature. What's the second thing we know? That's right, it's going to be the pressure. Our T2 is 15 degrees Celsius, and our P2 is equal to P1, and that is known as 90.4 kilopascal. Okay, so those are the 2 things we know.